effect on any one particular point. Say just charge with QT. Just charge with QT. It is a neutral one. It is not having any charge. Now this is the body, charged body. This effect is how much it is there on the body. That effect is, that strength is denoted by letter E bar. That denoted by letter E bar is nothing but electric field intensity. So electric field intensity is equal to what here? Electric field intensity is equal to force existed by the Hertz charge. Force existed by the Hertz charge. So because of only this charge we are going to consider, means that's why we depend with the limit QT tends to 0. QT tends to 0. So from this we can say electric field intensity units are newtons per coulomb. Already we discussed there in the introduction. Newtons per coulomb. And that too, this electric field intensity effect, how much distance it is having. So that distance, generally electric field intensity units should be defined with volts per meter. The voltage magnitude based on distance. If distance is more, means electric field intensity effect will be less. That's why transmission lines, insulators will be discussed already. Transmission line insulators will be, the distance or number of insulators will be provided based on the magnitude of electric field intensity or the voltage. Electric field intensity or the voltage. So next is electric flux density. Electric flux density. Electric flux density denoted by letter D bar. Electric flux density, it is electric flux density. The flux density, how we can define? It is the amount of electric field passing through any, the amount of electric field passing through any given surface. Electric field density we can define as the amount of electric flux, the amount of electric flux passing through a given surface area. Then we found the definition how we can define electric flux density is equal to electric flux by surface area. Electric flux by surface area. Surface area units are what? Meter square or centimeter square units we can define. Electric flux generally meters we can define. Centimeter divided coulombs. Flux units are what? Coulombs. Electric flux units are coulombs. Flux density units are coulombs per meter square. Coulombs per meter square. Electric field intensity depends on the medium. Electric flux density is what? It's independent of medium. Independent of medium. Electric field intensity is electric field intensity. It is depends on the type. In the area, in the air, the flux line, in the air field intensity will be something. If you provide any medium, it will changes. That's why between the between the cross arm to the conductor, we are going to provide with a circular disc shape like this. This type of disc shapes. We are going to place it from the tower. It is the cross arm charging. From the cross arm to certain discs, we are going to place it your power conductor. Our power is the conductor. Conductor means how electric field intensity should travel from the conductor. We will travel like this. If distance means provided, means that length to the path to the ionization is increased. If path to ionization increase means resistance increase means current flow decreases. These currents also, of course, these currents are called leakage currents. Because of ionization, the current flows is called leakage currents. So that's why it is electric flux density is independent of the medium. Suppose if at any one particular point, the flux density, how it can define from the definition, at a particular point, flux density is equal to d psi by dx. Psi is that what you can define with electric flux density. Suppose if you want the flux, how you can get flux? If you integrated d bar dot dx. That integration is what? Surface integration. It is nothing but double integration. double integration of d bar into ds bar is nothing but we can get electric flux. All these we'll see in depthly in the subject while discussing about the subject. Just like we were doing introduction only here. The next, magnetic field intensity. The next definition is magnetic field intensity. Magnetic field intensity. So magnetic field intensity is denoted by letter H bar. The magnetic field intensity is denoted by the letter H bar. See what is magnetic field intensity? It is nothing but the total, the amount of magnetic flux passes through a given surface. Is nothing but the definition of magnetic flux, magnetic field intensity. So the magnetic field intensity is different. Magnetic flux intensity is nothing but it is a measure of magnetic field intensity. It is a measure of the strength of magnetic field on a particular point, any one particular point. If you observe what is the strength of the magnetic field, and that is defined by the magnetic field intensity. This magnetic field intensity is independent of time, independent of medium. That's about magnetic field intensity. Next, magnetic flux density. Magnetic flux density. Denoted by letter B bar. It is nothing but what? It is nothing but the amount of magnetic flux passes through a given surface area. So from the definition, how we define magnetic flux density? B bar is equal to flux, magnetic flux divided by surface area. Magnetic flux we define with the letter I divided by A. Flux by area. Flux units are what? Weber. So we studied already Weber. Divided by area units are meter square. So magnetic flux density units are Webers per meter square. So you can't read all the time Webers per meter square, Webers per meter. That's why you can say simply these units are Tesla. Magnetic flux density. If a differential magnetic flux, d bar is equal to what? d pi by ds. So this flux we can calculate by using double integration of v bar dot ds. This is about the magnetic flux density. Or it is depends on the medium. Flux density depends on the medium. Flux density, because the flux may be changed. If any through the wood, flux traveling is less. Through the air, flux traveling is more. This is about the magnetic flux density. If you differentiate these two, electric field and magnetic field, if we differentiate electric field and magnetic field, because sometimes the exam asking the differences between electric field and magnetic field also. That's why I'm going to differentiate between electric field and magnetic field. Here, the first the units for electric field here, the strength we define with the electric field intensity. So electric field intensity, how you are going to define it? Volts per meters or newtons per coulombs. And here, magnetic field intensity units are what? The magnetic field intensity units are what? magnetic field intensity. Magnetic field intensity units are webers. Flux per webers. Sorry, current is flowing because of sorry. Flux is actually because of current, and magnetic field intensity will be with differentiate of how much distance it is having. So amperes per meters. So electric field intensity units are volts per meters. Magnetic field intensity units are amperes per meters. Here, flux density. Electric flux density denoted by letter B bar. Those units are what? B bar units are what? Coulombs per meter square. And here, magnetic flux density, how you are going defining? B bar with units are Webers per meter square, or simply Tesla. Here in this electric field, constant we define with permittivity. Denoted by letter epsilon. Here we use permeability. Denoted by letter mu. So epsilon we define with epsilon is equal to epsilon r into epsilon naught. Epsilon naught is relative permittivity. Depends on the material. Epsilon r is equal to 1, we know, for what? Air. And epsilon naught is equal to the constant we define with 8.854 into 10 to the power of minus 12 farads per meters. And here permeability we denote with the letter mu. Mu is equal to mu naught into mu r you define. This mu r depends on the medium. Generally mu r is equal to 1 for air, and mu naught we define with 4 pi into 10 to the power of minus 8 Henry per meters. 4 pi into 10 to the power of minus 8 Henry per meters. Here epsilon affects only on electric field. Here what? This epsilon effect is on only electric field. This effect is not on magnetic field. Similarly here, that the effect of mu is only on magnetic fields. This effect is not falls on the electric fields. Permeability effect. These are about the differences between electric field and magnetic fields. These are the difference between electric field and magnetic fields. Now, so electromagnetic model is deals with only 4 concepts. One is electric field intensity, another is magnetic field intensity, another is electric flux density, and the magnetic flux density. To study about these, we are going to using 2 mathematical tools. Those are, one is coordinate system, and the second one is vector calculus. We are going to study about these 4 concepts of this electromagnetic model. To study these, we are going to using 2 mathematical tools. Those are coordinate system and vector calculus. So in these 2 mathematical tools, how electric field will varies with respect to time to time, and we will see. If you go to coordinate system, again how many types of these coordinate systems? Only we study mathematics basics. These coordinate systems are of 3 types. Those are, first one, Cartesian coordinate system. And the second one, cylindrical coordinate system. Third one, spherical coordinate system. About these coordinate systems, Cartesian coordinates, cylindrical coordinate system, and the spherical coordinate system. What are the axes lies in Cartesian coordinate system. Why this all the systems we are going to use? You may get doubt here. All these systems are related to three-dimensional views. What I said, if current is flowing through any conductor, surround the conductor, magnetic field will develop. Surround the conductor, magnetic field will develop. That magnetic field effect is in which direction? We can say all the directions. So all the directions, how we can define? All the directions we define with a three-dimensional view. Two-dimensional view, you can see with our eyes. We can see two dimensions. This is x-axis. This is a y-axis. This is called two-dimensional view. So are you able to see the two axes at a time? Yes, we can see the two axes at a time. We can see the two axes at a time. Suppose if I place any other axis, z, three dimensions. Is it possible to see the three lines at a time? It is impossible to see the three lines at a time. If you try to see for long period, your eyes will affect. That's why you can't able to see three-dimensional views. We can't able to see three-dimensional views. To see three-dimensional views, to reduce the effect on the eyes, we are going to using some special spectaculars. Remember, on the universe, one-dimensional views is there, one direction, two-dimensional views you can see, all the directions are three-dimensional. So only three-dimensional. There is no 4D, 5D, 6D. Somewhere you are going to listening, say 360 movies, 70 movies, I don't know how it is mean. The other directions are about three-dimensional. Only up to three-dimensional views they are having. So this. What I said, electric field, magnetic field will traverse in all the directions. To know the electric field is how it is varying with respect to time through the medium. To know that, we are going to study about coordinate system. In that coordinate system, again there are three types of systems. One is Cartesian coordinate system, cylindrical coordinate system, and a spherical coordinate system. In Cartesian coordinate system, we can represent with, of course, every system is having three axes: x, y, z axes. X, y, z axes. So this x-axis, what is the length of this x-axis? We can say the x varies from minus infinity to plus infinity. Similarly, the length of this y-axis also, minus infinity to plus infinity, and the z-axis length also minus infinity to plus infinity, to plus infinity. In coordinate system, what I am doing, we are using three axes: x, y, z. Next, go to cylindrical. In cylindrical coordinate system, there are also three axes are there: rho, pi, z. These are the axes: rho, pi, z. Rho is nothing but the radius of the cylinder. So radius of the cylinder. Generally, in one cylinder, one particular point. If radius is 0, is nothing but just point. Now, if there is a radius, means from origin to you have to represent. Means this is starting point 0. So 0 to infinity gets. That's why the range of rho is 0 to plus infinity radius. Now, if radius is there, means you can represent. See these axes also similar to x, y, z axes in the Cartesian coordinate system. This pi is nothing but the angle made by the positive x-axis. The angle made by the positive x-axis. If you it means if you take any one particular point on the cylinder, if any one particular point, see this radius is same rho. So angle made from the positive x-axis to that radius path, that angle is denoted by letter pi. So generally this pi varies from what it is like circle. So pi varies from 0 to 0 to 360 degrees, 0 to 360 degrees, and z is similar to in Cartesian system. This is varies from minus infinity to varies plus infinity. So z varies from minus infinity to plus infinity. Next, if we think about spherical coordinate system, in spherical coordinate system, sphere, it is like globe. So actually this is like globe, sphere. So in spherical coordinate system also, they are same like this. Also three-dimensional view. Spherical coordinate system, the axes are r, theta, pi. Pi is not same like but point located from minimum positive x-axis to the any radius part is specified. The angle made by the positive x-axis is called pi. And here theta is nothing but that extension point if you represented. That extension point from other axis. The other axis is nothing but theta. That's why the range of theta. Remember, in depth we will discuss about each and every coordinate system in depthly. there you can understand clearly. So here this R radius is represented with 0 to plus infinity. So theta is represented from 0 to pi, 0 to 180 degrees. Pi is similar to cylindrical. So pi is equal to 0 to 360 degrees. This is about Cartesian. This is about Cartesian cylindrical spherical coordinate systems. So next class I can explain very clearly in depthly about what is coordinate system. When what are the characteristics of Cartesian coordinate system? Means what properties it is going to be accepting. Similarly, cylindrical, spherical. We will discuss about in depthly all this, and after that, after knowing some already you studied all this, even though once again I can explain. And now we will explain. We will apply all these mathematical tools to on our electromagnetic field subject. Electromagnetic field subject. And similarly, vector calculus also we are going to use it to determine the variation of flux from medium to medium. To know the variation of flux from medium to medium, we are going to using vector calculus mathematical tool. This is also one mathematical tool. Now in your regular syllabus, first 2 units. 3 units you are going to study about static electric fields and static magnetic fields. About these two you are going to study in first 3 units. In the 4th unit we are going to study about dynamic fields, time varying fields, means electromagnetic fields. About electromagnetic fields, dynamic or electromagnetic fields. We are going to study about dynamic or electromagnetic fields in 4th unit. In the 5th unit, we are going to study about wave propagation. Wave propagation means how fields will travel through the air. We discussed already. Air is a conductor. If anyone asked, air is a conductor or insulator, as an electrical engineer, we have to say first you have to ask for frequency. If frequency is low, means less than 100 or 50 Hz, current or electric field will travel through the conductor through medium. If for high frequencies means like kilohertz or megahertz frequencies, we are sending power, electrical energy or power through the air. That power is low power. Low power means very less power. That much less power. That less power means less voltage, low currents. Human beings can't affect any current, shock effect. So that's why low power levels we are going to transferring through the air. That's why if anyone asked if air is a conductor or insulator, we have to say directly whether it is a high frequency levels or power frequency levels. Power frequency levels, air is a insulator. For high frequency levels, air will work as a conductor because ionization will form on the conductor. Radiation, it's called radiation. Due to radiation, current power travels through the air. You remember that a human body, generally if a healthy human body, if current is less than 10 milliamps, we can't feel any shock effect. If current levels are more than 10 milliamps, we feel shock effect. So in that wave propagation, in this wave propagation by using pointing vectors and pointing theorems, how power levels will changes, we will study. This is about the symbols of electric field intensity. So next class we will discuss about coordinate and vector coordinates and vector calculus in depth. I'm stopping here. Thank you very much. Yeah, before stopping, see here. What I said here, air is a conductor. I said for what? For high frequency levels. In the high frequency levels, you studied it. For high frequency air will work as a conductor. So air will work as a conductor means we are going to transferring signals or power through the air. Weak signals, those are called. That means low voltages and low current state. That current state is what I said, less than 10 milliamps. That current states are less than 10 milliamps. If current is less than 10 milliamps, voltage levels are generally 5 volts, 2 volts, 6 volts, something we are going to electronic. These are called electronic fields. So we are going to do all this in electronics. Then we are going to use some switches, particularly it is a transistor diodes to work for low frequency, low current. So the same switches we are going to using in electrical engineering also. Those switches we are going to call those as power switches, power switch like power diode, power transistor, or you can call power diode, power transistor. So this is about our syllabus structure: static electric field, static magnetic field. So we are going to study in first 3 units. The 4th units we are going to study about time varying fields or dynamic fields or electromagnetic fields. Here completely on Faraday's law. We play with the Faraday's laws. Faraday's laws here. Faraday's laws. And here in these 2 units, how ionization will exist. To avoid ionization, what we have to do? What precautions we have to do? Because of ionizations, what parameters will exist? You may study about capacitance, how capacitance will form. Here in static electric fields, we are going to study. In the wave propagation, we are going to study how power transfers. I said already through the air by using pointing vectors, pointing theorem, we define how power will transfer through the air. This is about the structure of the total syllabus. You know what is Faraday's law to study? What are the Faraday's laws? How many types of Faraday's laws we are having? 2 types of Faraday's laws we are having. 2 types of Faraday's laws. Faraday's first law and Faraday's second law. We are going to say the importance of Faraday's laws is Faraday he only prepared the electrical energy. He only prepared the voltage source. Electrical energy is nothing but preparation of voltage source. If there is a voltage source, if a product goes apart to the any load, current starts to flow. So product of voltage and current is power. We are going to say. So the time, if you are applied for 1 hour into 1 hour in that, but we can define energy. That's why preparation of electrical energy or preparation of electric power is nothing but preparation of voltage source. So to prepare voltage source, what are the basic requirements required? Conductor and magnetic field. Conductor and magnetic field. And between these two, one condition will be there. Either conductor has to rotate or magnetic field has to rotate. With respect to space, space means anyone has to rotate. So to rotate anyone, we are going to giving mechanical energy to the generator. So to prepare electrical energy, we are going to using the machine generator. Means if you given electrical energy to rotate anyone conductor or magnetic field, we are going to give mechanical energy and we are going to getting electrical energy. We are going to getting electrical energy. So from Faraday's first law, you are going to do how electric fields we are going to making by using mechanical sources. And Faraday's second law is saying how much amount of voltage we are going to preparing. So how much magnitude? It represents the magnitude for voltage source. Depends on number of turns, depends on flux, depends on speed. Voltage magnitude will depends. So these are Faraday's laws. In electric field, how Faraday's laws are useful. There we will study in 4th unit. Okay. This is about silver structure. So here we start. See Faraday's laws we discussed, and in the Faraday's law, what I said, from the Faraday's first law, we are going to preparing voltage source. Voltage source is having positive terminal and negative terminal. To know that voltage source positive terminal and negative terminal, we are going to using Fleming's right hand rule. What Fleming's right hand rule is saying? You study Fleming's right hand rule. If you placed for the Fleming's right hand rule, what are the input? Flux and the forces. Flux and mechanical energy. With that, you are going to get electrical energy. That electrical energy, how you can define with the middle finger. Here, here for the Faraday's law, to prepare a voltage source, the inputs we are going to giving as forces, mechanical forces, and the flux. Flux if you represented with 4-finger, and mechanical forces if you represented with the thumb, then the middle finger indicates the direction of current only. So based on direction of current, if those currents are entering into any part, to flow current what? We have to provide must be closed path to the conductors. If you provide a closed path with any one resistor, if currents are entering to that resistor, that entering terminal we can define with positive terminal, leaving terminal we define with the negative terminal. So based on by knowing the current directions, we represent the voltage source polarity. Otherwise, you can't represent the polarities directly, which is positive terminal and which is negative terminal of the voltage source. It is impossible to represent the polarities without knowing currents. That's why to flow current, we have to provide a closed path. You may get doubt why we are going to preparing voltage source only, why we are not preparing current source. We are preparing voltage source only. That's why we are going to see everywhere voltage source practically. There is no current source practically. Current sources we are going to study theoretically only. Remember, for this proof we can understand later. Later, it is not possible to apply because you need to gain some more knowledge in engineering. All our loads are resistive and inductive loads. In your home loads, some fans you are having, some lights you are having. Lights are the examples for resistor loads, resistive loads, stationary loads, static loads. All the rotating fans, mixes, washing machines, all those are called rotating loads. Those are examples for inductive loads. Flux related loads, inductive loads. So all our loads are resistive inductive loads. For resistive inductive loads, voltage source with this time, current source not with this time. That's why we are going to be preparing voltage source only. So we are going to studying practically voltage source. Practically, remember, there is no current sources. Not only current source, there is no capacitive loads practically. This is about small introduction about this subject. So next class we will discuss about all the coordinate systems in depth. I am stopping here. Thank you very much.